We're starting a new lesson today. This is over Lewis structures and formal charges. I am getting this out of an AP chemistry textbook. So title this AP Chem. This is Chapter 8, Sections 5 through 7. And before we get into it, because with our Lewis structures, we're refreshing your memory on valence electrons. Based on what group that element is in, you need to know how many valence electrons it has. These are the outermost electrons available to be lost, gained, or shared in the formation of a compound. So if we look at group 1, we have 1 valence electron. Group 2 is 2. Jumping over to group 13, hopefully you see the pattern here. We've got 3, group 14, 15, 16, 17, and group 18. So those numbers in orange are the valence electrons. Have a periodic table handy. You're going to have to look back at multiple elements today and count up a lot of valence electrons. So here's an example of 2 Lewis structures that represent molecules. It's going to show all of the electrons, bonding and non-bonding. I'm hoping that at least the Lewis structure part of this is a refresher for you from last year, and then the formal charges will be the new information. So starting off, please get all of your steps written down for drawing out a Lewis structure. Step number 1, you find the sum of valence electrons of all the atoms, either in the neutral compound or the polyatomic ion. If it is a polyatomic ion, you know, ions can have positive or negative charges. So if it's an anion, meaning a negative charge, you subtract or add 1 electron for every negative charge you have. So if you're dealing with a sulfate ion with a 2- charge, you would add 2 extra electrons to your total. And then if it is a cation, cations have a positive charge, meaning you've lost electrons. So you would have to subtract off an electron for every positive charge you have. So if you're talking to the ammonium ion that's a +1, you would subtract 1 from your valence electron count. In this example, we're dealing with PCl3, so phosphorus trichloride. Phosphorus is in group 15, so 5 valence electrons. Chlorine is in group 17, so again, that's the group that they are in. So it has 7 valence electrons, but there are 3 atoms of chlorine. So 3 times 7 is 21. You add that up, we have 26 total valence electrons that we have to find a home for. So when we do get in class and you're drawing out Lewis structures, you're going to go through every step, show the math, show every piece that you would do. So step 1, show me the math. How are you getting those valence electrons? Step number 2. The central atom is going into the middle of our Lewis structure. The central atom is usually the singular atom too. In this case, we just have 1 phosphorus versus 3 chlorines. But let's say that you have 2 singular atoms, then your less electronegative element is going into the middle or central part of the structure unless it's hydrogen. Hydrogen's never in the middle. And we form bonds. We start with single bonds. A bond represents 2 electrons. That bond, which is our dash, there's 2 electrons, 2 more, 2 more. 2 plus 2 plus 2 is 6. So we keep track of our math. We subtract off 6 from our total. We now have 20 electrons left over to find a home for. 20 electrons left over to find a home for. Step number 3, we fill the octets of the outer atoms. We will go over exceptions to the octet rule, but you've learned that an octet, that mainly means that your outer energy level is going to be filled. Group 18 has 8 valence electrons. That is what is so important for their stability, and a lot of atoms want to be like the noble gases as far as stability goes. So each of those dots represents 1 electron. And if you count up, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 18 electrons that we're now going to subtract from our total. We have 2 electrons left over to find a home for. And again, do not put dots in the same vicinity as your dash. Do not put them in the same location. That is step 3. Step number 4. You fill the octet of the central atom, assuming that it needs an octet, and we'll go over, like I said, we will go over exceptions. So those last 2 go on phosphorus, which gives it 8. So we have 2, 4, 6, and again, those are being shared with the chlorines. 7 and 8 are on top, so it also has 8 valence electrons. We're switching examples on you because we need to get to step 5. Step 5 says if you run out of electrons before your central atom has an octet, then you have to rearrange your molecule to form multiple bonds. That could be a double bond is being formed, a triple bond is being formed. But let's go through the math of what they're talking about here. So we've got HCN, 1 hydrogen, since it's in group 1, has 1 valence electron. Carbon is in group 14, it'll have 4. Nitrogen is in group 15, it will have 5, so we need to find a home for 10 electrons. And as I look at this, I see 2, 4, 6, 8, 10, because we've gone through all the steps so far. We've used up all 10 electrons, and nitrogen has its octet of 8 around it, but carbon only has 4. Carbon will always have 8, but we cannot just randomly add extra electrons. But at this point, we will rearrange the electrons we've distributed to try to get them set up in a way so carbon and nitrogen are both satisfied with 8 while sharing. So you could erase these 2 electrons at the bottom. Might have to be a little bit inventive here. Erase these. That's not really erased, but they're going to come over here. The dot dot, which makes another dash for a double bond. If you were to count, nitrogen still has 8 around it, but now carbon's up to 6. We would have to erase the top 2 right up here. Bring them around. Dot dot. There's a third dash. Those 3 dashes represent 6 electrons, and that will satisfy both parts. So there they're showing you the electrons being pulled around where you're going to have a triple bond. And as I look at the final answer over here, your carbon has 8 electrons around it, 4 dashes, that's 8 electrons. Nitrogen has 8 around it. And when we look at bonding and non-bonding pair, those that are bonded are your dashes. If they're non-bonded, they are the dots. Now we're going to assign formal charges. Formal charges also help you to know if it looks like there's more than one option in drawing out your Lewis structure. Formal charges will help you determine what the correct option is. When we look at carbon dioxide, and we're going to go through the math real quick with it, CO2, carbon has 4 valence electrons, oxygen has 6, but 6 times 2 is 12, so a home for 16 electrons. When you originally draw it out, C bonded to both of your O's, that uses up 4 electrons. We have a home for 12 more. Those 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Those 12 are used up there. We would have to go through and start to rearrange because even though each oxygen has 8 around it for an octet, carbon only has 4. What you see highlighted in blue is showing you the 2 options for rearranging, and both of them look really good because carbon has 8 around it in each case. Our oxygens are happy with an octet, but only one of them is the correct structure. So we assign formal charges. With the formal charges, you're going to count the electrons in your lone pairs, and half the electrons it shares with the other atom. And then we'll subtract that from the number of valence electrons that that element actually has. Please make sure that you get this in the correct order. So valence electrons. Notice that the top numbers in both cases are the same because it's based on the group it's in. Oxygen's in group 16, it has 6. Carbon's in group 14, it has 4. But when we do the other math part of this, it's a little bit different. For the electrons assigned to the atom, we are looking at oxygen first. So right around this oxygen, I see 4 dots and 2 dashes. So 4 plus 2 is 6. That is the same on the other side. But then our carbon that is in the middle has 4 dashes, so it gets a 4 because that's where it talks up above that. You get half the electrons it shares. So a dash, you're only going to count half instead of the whole for your formal charges. On the other side, we have oxygen here, 6 dots, 1 dash, 6 plus 1 is 7. Oxygen on the other side, 2 dots plus 3 dashes, 2 plus 3 is 5. And then carbon in the middle, it still has 4 dashes around it, so it gets assigned a 4. And when you subtract it, you get formal charges of 0, 0, 0 in your first option, but formal charges of -1, 0, +1 in the second option. I'm going to give you a few other rules to go by as you're looking at this. First, the sum of your formal charges equals 0 if it's for a neutral compound. So that is what we are looking for a neutral compound. You want the sum of your formal charges to be equal to 0. The second one, the sum of your formal charges is equal to the charge of the ion. That is what is preferred for your polyatomic ions. So if the sum of all your formal charges equals the charge of the ion itself, that is the preferred Lewis structure. And then, like I said, we will get to expanded octets. We're going to go ahead and touch on it now. Only expand your octet if that is the only option to distribute all of the electrons, even if the formal charge appears better. So again, only expand your octet if that's your only option to distribute all electrons, even if the formal charges appear better. So get those written down. We're going to go look at another example. In this one, it's saying the best Lewis structure is the one with the fewest charges, and it puts a negative charge on your most electronegative atom. Again, just some refreshers as you're going on through here. Electronegativities, they increase across the period. So fluorine is your most electronegative element. Kind of ignoring the noble gases over there, but as you move across the period, electronegativities increase. If we were to look at the calculations for our formal charges here, let's do valence electrons first. So for nitrogen, group 15, it has 5. Carbon is in group 14. Oxygen's in group 16. So we can write that down for each of these. And then we're subtracting off the number of electrons that are around that particular atom. Lone pairs, count them as is. If they're shared, though, that's your dash. Just count half of it. So for nitrogen, I see 6 dots, 1 dash, so that's a 7. Carbon, 4 dashes. Oxygen, 2 dots, 3 dashes. In the next example, nitrogen, 4 plus 2. I see 4, and then 4 plus 2 again. And then the last one, 2 dots, 3 dashes, 4 dashes total. And then the last one, 2, 4, 6, 7. 6 dots plus 1 dash, that is 7. And we're going to subtract each of these. Now notice that this polyatomic ion has a negative charge to it, and the one in the middle, the one on the right, both end up with a -1 charge overall, which is great. But it says if it puts a negative charge on your most electronegative atom between nitrogen, carbon, and oxygen, which all happen to be in the same period, oxygen is the most electronegative of those three. Our negative is on the oxygen in the last option. So that is our correct answer. Getting into resonance structures, a resonance structure, resonance means to resonate or move back and forth. You'll have resonance structures with some of our compounds that have multiple bonds, but you need a multiple bond so that we can resonate. And in this example, this is ozone, O3, and there's the Lewis structure for it. But hopefully you realize we could have easily drawn this like that, where the double bond appears to be on the other side. So that set of electrons, the double bond here versus the double bond there, those electrons are flipping back and forth between those two positions because it is resonating. Okay, so resonance structures can happen, but if they're going to happen, you do need a multiple bond, but that is not always the case as far as a multiple bond does not always resonate. So now they give you a little more information here, and they throw in some information about the charges being a fraction, and this is what your ozone is going to look like. So one Lewis structure is not going to accurately depict a molecule as ozone. It's showing the two that I just showed you earlier. And it's just giving you another example here. Just as green is a synthesis of blue and yellow, ozone is a synthesis of both structures. You will see them both occur basically 50-50. In this example right here, you've got your CO. If you are going to have those electrons resonating, it's got to be between identical atoms. So for other reasons too, you're not going to see that double bond resonate to the hydrogen, but it will resonate between your two oxygens. And to try to find that Lewis structure, do it yourself. Calculate up your valence electrons. Make sure you can come up with it. And within a resonance structure, we say that those electrons are delocalized, meaning they are moving. They are no longer local to one spot, so delocalized. And we have another one here. It's an organic compound of benzene. So probably the first time you've seen a benzene ring. But within that ring and that structure, we have 3 different double bonds. And notice between the left and the right, those double bonds can switch which position they are in. So you will commonly see, whenever we get to the organic side of things, that last structure with the circle in the middle. So the hexagon with the circle, you do the circle, it represents, yes, I have 3 double bonds, but because of the resonation that's going on, that's its best picture that we use. Moving on to exceptions to the octet rule. There's 3 types of ions or molecules that do not follow it, and those are going to be those with an odd number of electrons, which we will just briefly talk about now, but I don't plan on giving you examples of those. Those that should have less than an octet, and those that will have more than an octet, we call it an expanded octet. Again, the odd number of electrons, which I don't plan on giving you. These are going to be very unstable. We're not going to talk much about those. Now, fewer than 8 electrons. Let's talk about those that should have fewer than 8. And I throw in here any element that is in group 1, 2, or 13. Any element in group 1, 2, or 13. That includes hydrogen too. Here's how those work. The number of valence electrons that group 1 has is 1. Group 2 has 2. Group 13 has 3. Within a Lewis structure, that's how many electrons they're allowed to pair up with. So if, I'm going to change my color again. Within the Lewis structure, group 1 has 1 valence electron. It can pair up with 1 for a total of 2. Group 2 has 2. 2 plus 2 is 4, so it'll have 4 within the structure. If it's an element that you're working with, it's out of group 13. It has 3 valence electrons. It can pair up with 3 others for a total of 6 within the Lewis structure. So these are examples of an exception to the octet rule, but on the fewer side. Those that can expand, and we're going to try to limit it to a few here. We're going to concentrate on sulfur, phosphorus, xenon is also thrown into there. But the common expansion that you're going to see for these, sulfur has 6 of its own valence electrons, and it can pair up with 6 more for a total of 12. Phosphorus has 5 of its own valence electrons. It can pair up with 5 more for a total of 10. And what I want to say about the expanded octet is you will find often sulfur and phosphorus are part of molecules where they do not have an expanded octet because their formal charge, it works out best that you don't expand it and all the electrons have found a home. But if they do expand, that is their common expansion number that you would be looking for. So those are a few elements to keep your eye on, that it is common for them to expand. In this example, boron trifluoride, notice they are showing you boron here, and in each case it looks like you've tried to double bond to B, but boron is in group 13. We just said group 13 will have fewer than 8 valence electrons. So these formal charges you've come up with here are not going to work because fluorine is your most electronegative element, and it keeps putting a -1 on boron, which is not the most electronegative element. So with this one, the most important structure is going to be what you see there on the left. Boron has 3 valence electrons. It can pair up with 3 more for a total of 6. Remember, each dash is 2, so it is happy with that structure. And then the lesson, filling the octet of the central atom results in a negative charge and a positive charge on your more electronegative outer atom, then do not try to give it an octet on the central atom. Here's an example of one of our expanded octets. Phosphorus is there in the central area. If you were to count up all of your valence electrons, phosphorus in group 15 has 5. We have 5 chlorine atoms, and each of those has 7 valence electrons, so 5 plus 35 is 40. You would have to find a home for 40 electrons, and in this case, the best option is let's have 10 electrons around phosphorus. You see your 5 bonds there for a total of 10, and that is its best case scenario. And it throws a little more information in there about what electrons are actually involved in these bonding. Since it is allowed to bond and your phosphorus is in the 3rd row, it's saying presumably your d orbitals in these atoms participate in bonding. So it's not just your s and p orbitals anymore, but your d orbitals also. In this one right here, it shows you phosphorus with 4 oxygens. And as we look at the phosphorus with the 4 oxygens, it's throwing the formal charges on these. This is the phosphate ion, PO4 3-. And the better structure is going to put the double bond between the phosphorus and the one of the oxygens as far as formal charges goes. So when the central atom is on the 3rd row or below and expanding its octet eliminates some formal charges, that is the way you need to proceed. So again, it looks like everything looks good on the left. You've distributed all your valence electrons, but when you take that extra step and you look at formal charges, the best option is actually what you see on the right.